Hi, my name is Aliyu, and I'll be presenting our paper using Markov decision process to model deception for robotic and interactive game applications, which has been accepted at IEEE ICCE 2021. So deception has a long history in the study of intelligent systems. Um, Humans and animals alike both use it for different form of advantages in their social environment. For example, animals like grasshoppers use that for survival to, deceive the predators. Um, so what is deception? Deception imparts wrong information or just conceals it completely. So similar to humans, robots can also use deception for different advantages. Major applications of robot deception include military, different kind of computer games, and even social robot situations. In this paper, we deal with robot deception from a motion perspective and for multiple interactions with a human. And our hope is that it will enhance entertainment in different interactive situations, in particular computer games. So there has been limited work done on robot deception. In particular, one of the closely related work is the one done by Dragan et al., in which they use a robot deception from the motion perspective as well, but more like a humanoid robot that uses three different kind of deception strategies like this to pick up two different targets and try to deceive a human in which target is being picked. Um, However, they had a lot of limitations, specifically that it was only applicable for a single interaction with a human, and if the human interacts with the robot again, they would be able to recognize the strategy and they won't be deceived. Um, Wagner et al., they presented a game theory-based approach for robot deception in which they decide even when to deceive. However, that was also only applicable for deceiving other robots and not humans. In this paper, we consider the deception as a memory problem in which we can remember the previous information and decide how to deceive the other person or human and we represent it using Markov decision processes. Markov decision process has been used before for memory problems, and it has been in some capacity used for deception, but not for particularly for robot applications. Um, so our first goal in the paper was to actually use as a mobile robot simulator and use the three deceptive trajectories presented by Dragan et al. And apply it on a mobile robot simulator with two targets. And we use the three different strategies that they developed: exaggerating, switching, and ambiguous. We also use a version 2 of the strategies in which the robot actually moves back to the other target after it has reached the initial target, which has been shown to increase deception in the studies used by Dragan et al. Then we lastly also add optimal strategy, which is simply not deceptive at all on its own, but we believe or we hypothesize that this will also be deceptive when the human interact with it while interacting with these other strategies. So as I said before, we use Markov decision process to memorize the previous strategies and decide which strategy to choose to deceive a human based on all the previous interactions with the human. So essentially, it can be represented as a Markov chain. And in our case, there are four initial strategies to choose from, like the optimal strategy, exaggerating, switching, and ambiguous that I showed before. And the version 2 of the strategies can be chosen after the initial strategy has been chosen. So for example, exaggerating has been chosen, and then it can be the version 2 can be chosen similar to another Markov chain. So essentially, the probability of choosing a deceptive strategy at a particular interaction is dependent on all the strategies chosen in the previous interactions. So one of the issues with Markov decision process is that it can lead to memory constraints because of infinite Markov chains. So in this case, one way to deceive is using a random variable, like using randomly choosing a strategy. However, that's not an optimal algorithm for deception because as we show in a small experiment that if we run this, if we choose these four strategies randomly for 20 different directions, some of them are chosen a lot more times than the others, which means there will be a lot more repetition of those strategies, which means humans won't be able to get deceived when there is that repetition. We also did an entropy analysis of the random algorithm. We call that the random algorithm. And it showed that the overall entropy of the system is 1.79, again with the same experiment of 20 interactions, which is much lower than the maximum value of 2, showing that the random algorithm is not optimal for deception in multiple interactions. So another way to solve this problem is to have a fixed number of times a state occurs in 20 interactions. There are two ways to do that, and one is that you just fix a state to occur every 4 interactions, or you can choose it to occur a total number of equal number of times, but it can occur as many times in 4 different interactions. However, it leads to same issues of similar kind of pattern that can be assessed or that can be recognized by a human, and they won't get deceived. However, the entropy of the system is 2.0, like the maximum, because all the strategies occur at the same time. It's just that it's not deceptive. So because of this, we design an adaptive algorithm in which it's kind of a combination of the both random and fixed algorithms. So at each interaction, whenever a state occurs, we actually transition some of the probability of that state to the other state that have not occurred or have occurred less than that particular state or strategy. So in this way, there's a hyperparameter lambda, the transition probability transition parameter, that actually decides how much probability is going to be transitioned. In this case, at each interaction, there is still a chance of a state to occur, even if it has occurred before multiple times, but it's much lower. It's not 0 because it's not a fixed algorithm, and it's not like 1 by 4 because of 4 states, because it's not a random algorithm. So we choose lambda is equal to 0.5 in this experiment just to have a compromise between random and fixed algorithms. And by using the same algorithm on the same experiment that we did for 20 interactions, we see that all the states occur almost equal amount of times, and the entropy is 1.98, which is almost perfect. And there is limited repetition of states, which means that this is the more optimal algorithm. We hypothesized that this would be a more optimal algorithm. Then to actually check our algorithm again using a user study, we designed a GUI, a very simple GUI, in which there are 2 targets. There's a mobile robot simulator, and then it moves towards different one of the targets, and the human can actually use the pad over on top using arrow keys to move towards one or the other target to show what they're predicting at each instant of the full interaction. In this way, we get a continuous collection of data about an entire interaction, showing like what actually occurred during the full interaction in the human's head. So to rate deception, there wasn't really any particular evaluation metric before. So we actually proposed new evaluation metrics. One of them is error, and the other one is confusion. For error, we measured the distance of the pad from the true target, and which shows like how far away the human thinks that the actual target is. And the confusion, it actually measures the belief of the human in his or her choice of the target, and it actually measures the movement of the target, movement of the pad, because of the derivative in that equation. And that kind of shows like how much the human moves. So if the human moves a lot, that pad, that means that they are not very confident in their own belief. Which means that the higher this number, the more confused they are. So we performed actually 2 different human-computer interaction studies to compare the random and adaptive algorithms, and also analyze the adaptive algorithm. We chose 60 different participants from Penn State, and 30 were chosen randomly for the adaptive algorithm, and 30 were chosen for the random algorithm. And in each experiment, the human interact with our simulator for 20 interactions, and also, participants played with the robot for a couple of practice rounds to get familiar with the setup. And so we hypothesized that the adaptive algorithm is better the random algorithm in deceiving humans for multiple interactions. And we performed a two-tailed t-test analysis over the data collected in those two different studies to confirm that our hypothesis is correct. The table actually here kind of confirms that as well, especially looking at the later interactions, like from 14 to 20, we have major differences, showing that our adaptive algorithm is much more deceptive than the random algorithm. And we also like showed the actual values of those numbers, error and confusion metrics, and we see that, and this is average over all the participants, over 30 participants for both algorithms, and we see that error metrics for the adaptive algorithm are much higher, especially in the later interactions. Confusion metrics are actually very similar, um, uh, even in the later interactions. So that one didn't really change that much. But error metric kind of shows that adaptive algorithm was better at deceiving the humans. We also asked the participants after the interaction to rate on a Likert scale of 1 to 7, different ratings of entertainment, deception, and intelligence and trust. And as expected, the ratings for entertainment, deception, and intelligence increased for our adaptive algorithm-based robot simulator, and the trust obviously decreased because the humans don't trust it as much, especially in the later interactions. So we asked that in the start and the later, so in the start of the interaction, each interaction of a human, and at the end of the full experiment, and we see that that the entertainment and deception ratings obviously increased. So overall, we are actually the first to propose an approach to deceive humans in a long run of interactions. But to the best of our knowledge, there isn't any approach like that. The user studies results confirm the hypothesis that our algorithm does increase the deceptiveness of different strategies, um, uh, even if the human is familiar with them, even if in the initial interactions. And our results also confirm that there was an increased entertainment for the users when interacting with the deceptive robot. Um, and Obviously, there are limitations in our approach still. One is that we only use lambda is equal to 0.5, and we didn't try other values. The experimental design was still very simple because there were only 2 targets, and it wasn't really like a very specific game environment. And because of that, in our future work, we hope to add multiple targets in a map where it is more like a actual like a computer game situation, and which will hopefully will show more insights into our algorithm and our approach. Thank you. And if you have any questions, just let me know in whatever medium they're using.